Hi all, thank you all for coming. I'm going to talk a little bit about the work that Matrix Solutions, now called Montrose, has been doing in the past few months. So we know that groundwater in Southern Ontario is related to the lithology of the host rock. However, the Niagara Peninsula is an exception. We see highly mineralized fluids in this area and high concentrations of sulfate and hydrogen sulfide in this area. So we know that hydrogen sulfide is a problem in this area. We know that some of this hydrogen sulfide is related to legacy hydrocarbon infrastructure, especially in areas like Whitley and Forestry Farm Road. We know that these areas are highly impacted by H2S. This presentation is going to focus on the problem of hydrogen sulfide in the Niagara Peninsula and the processes that lead to the production of this gas in this area. So as we can see, the Niagara Peninsula is highly impacted by H2S. We have concentrations going up to, in this figure, 100 milligrams per liter, but last year we found some concentrations going up to 400 milligrams per liter. In this video, we see a spring close to Selkirk, and we see the contrast of the spring full of sulfur discharging in a creek that goes directly to Lake Erie. So we know that the H2S may be natural in this area, but it can also be related to human drilling activities and infrastructure that can either directly release deep H2S or more commonly bringing two incompatible materials together that react and produce H2S as a byproduct. These two incompatible materials would be methane and sulfate, and we see from the OGS geological maps that they follow pretty much the geology of the area. So methane is mostly located in the shales from the Dundee Formation, while sulfate is mostly located in the evaporites from the Salina unit. However, in the Niagara Peninsula, we see that these two materials coexist, and this is not naturally possible. So before we go into deep in the hydrochemistry here, I'm going to talk a little bit about the Niagara Peninsula in a regional context. So here we have the Allegheny Plateau in the US part of the Great Lakes that is the high hydraulic point and induces a hydraulic pressure in the groundwater flux. And then we see these 3 stars are the samples that are the places that we collected samples in the past year. And this area is the low hydraulic point in the area, and we see discharge of very mineralized springs in this area. The Queenston Formation underlines the whole peninsula at a depth of at least 200 meters deep as its center, and it goes even deeper as it moves to the south, to the US part of it. The Queenston Formation has a different type of sulfate that's found in other areas of the peninsula. It's a terrestrial sulfate, while the other sulfates that we see are more close to marine sulfate. When we check the hydrostratigraphy of this area going from Lake Ontario to the Allegheny Plateau, this is what we see. We see that the Allegheny Plateau is the high hydraulic point and is at least 400 meters higher than the lowest point, which is the Lake Ontario. The aquifers in this area are the carbonates from the Silurian and Devonian, and the evaporites from the Salina unit. So that would explain the high mineralization that we see in the waters from the Niagara Escarpment and the Niagara Peninsula in general. However, the aquifer composition itself won't explain exactly all the anomalous chemistry that we see in this area. So another possibility are the gas wells that were drilled in the area in the 1800s, and that would allow the deep groundwater to move vertically to shallow aquifers. And we see that some of the samples that we collected have a signature of the Queenston Formation that is at least 200 meters deep in this area. And we know that because this formation has a very unique signature that we're going to talk soon. Why do we see all these deep fluids rising in the Niagara Peninsula? So one clue is the high ground to the northwest. So here we have a topography map from OGS The red squares are the samples collected by OGS, and the green stars are the samples that we collected last year. And we see that they all follow this trend, which follows, which is where all the springs are, and we see that the topography to the northwest is higher. The topography in this area would act as a barrier for the flux. Another clue is the drift thickness, the overburden thickness in this area. So in this case, the dark green is the thinner overburden, and we see that all of our samples, they follow this trend line in the thinner overburden, which is also the optimal point of deep pressure relief in the area. So knowing that this area may present anthropogenic inputs, maybe the H2S in this area might be natural or maybe anthropogenic, we selected 2 study areas, the Norfolk Bee Creek area and the Jarvis Port Dover area, and we conducted 2 types of assessment, the water quality assessment and the gas assessment. So for the water quality assessment, we checked first hydrogen sulfide concentrations. After that, we also checked sulfate concentrations and if this would match somehow the geology of the area. We checked the coexistence of methane and sulfate because we know that this is not naturally possible. And we also checked sulfur isotopes as an indicator of exogenic deep source fluids from the Queenston Formation. So we know that the Queenston Formation has a way more depleted signature when compared to the other, to the marine evaporites that we see in the area. We also checked the chloride to bromide ratio as an indicator of a deep fluid. So chloride to bromide ratios are very good to fingerprint where the salts are coming from, if they're coming from septic systems, or maybe a deep brine or saltwater, seawater. In terms of gas assessment, we checked the dryness ratio, which is the ratio of methane to ethane propane. And we also checked the isotopes of carbon in methane. So we would know if this methane would be from a biogenic origin or from a thermogenic origin. So some of our data for water quality assessment. So here we see a graph of chloride bromide mass ratio against chloride concentrations. And the size of the dots are proportional to the chloride bromide ratios. So we see that the small dots are related to the petroleum well brine, which means that the bromide concentrations are higher than the chloride concentrations. And the opposite is true for the halite, which could be road salt, and also we have some influence of septic systems. And this is what we see in our area. We see that in the Bee Creek area, the ratios are very small, which is very close to what we would expect from a petroleum well brine. And in the Port Dover area, we see a mixture of it. We see influence of petroleum well brine, but we also see some septic system influences in halite and from road salts. In terms of methane, so here in this graph, we see the methane plotted in the chloride bromide mass ratio against the chloride concentration, and the sizes are proportional to the methane concentrations in the area. We see that the highest methane concentrations, they match what we would expect to see in a petroleum well brine, and it's pretty high in the Bee Creek area, and it's pretty variable in the Port Dover area. The sulfate concentrations are very broad, so we have high sulfate concentrations in geological units that we were not really expecting. For instance, this green, this dark green is the Dundee Formation, and we see very high concentrations of sulfate in this area, which we were not really expecting. And we see some sulfate in this yellow part, which is the Onondaga Formation, and we were expecting a little bit of sulfur, but not a lot. In terms of sulfur isotopes, so here we see a graph of sulfate against sulfur isotopes of sulfate. Most of our samples fall in what we would call the signature of pyrite oxidation, and also Devonian and Silurian carbon, the Silurian and Devonian units. and a little bit a mixture of both of them. But we also see some outliers, and these outliers are matching pretty much what we would see in a terrestrial evaporite. And where we see terrestrial evaporites in this area, in the Queenston Formation, that is at least 200 meters deep. So the only hypothesis that we can think about, like a fluid that is that deep coming up, is using old ancient legacy wells conduits to move up. So when we see the isotopic data of methane and sulfate, so in this map we see some, in the red squares are the exogenic sulfate, the sulfate that looks pretty much with the terrestrial evaporite, the Queenston Formation. And we see it in the Onondaga Formation, in the Port Dover area, and a little bit to the right of the site. And these black squares are what we would call the thermogenic gas, the thermogenic methane. And we see it in the Big Creek area, but also in some locations in the Port Dover area. The blue ones are the biogenic methane, the methane that is possibly biogenic. And we see a lot of it in the Dundee Formation, which is expected, but we also see some interesting points in the Onondaga Formation. So the conclusions of this work is that the exogenic sulfate that we see is possibly related to the Queenston Formation. These fluids move up through anthropogenic conduits into shallow aquifers. The hydraulic pressure originating in the Allegheny Plateau likely induces the northward flow. The chloride-bromide ratios show impact of this deep Appalachian Basin brine. And the HOS production is from sulfate reduction and is usually by natural gas by two main processes in this area. So in the Big Creek area, it would be deep methane moving into shallow aquifers that naturally contain sulfate. And in the Port Dover area, it would be deep exogenic sulfate moving into shallow aquifers that naturally contain biogenic gas.